Why is controlling VAE latent space so challenging for models? Imagine trying to organize a vast library where every book is a little different, but you want to find a way to arrange them so you can easily find and modify any one. That's similar to what models face when controlling the latent space of variational autoencoders. These models turn complex data into a compressed, abstract form, which makes it tricky to steer or manipulate. The core challenge is that the latent space is a condensed version of high-dimensional data, like images or sounds, and it needs to be both flexible and meaningful. The first big hurdle is balancing two goals. One is making sure the model can reconstruct the original data accurately. The other is keeping the latent space smooth and continuous so that sampling from it produces realistic new data. If the model focuses too much on reconstruction, the latent space becomes messy and hard to control. If it emphasizes regularization too much, the details can get lost, making the generated data less precise. Finding the right middle ground is a constant challenge. Another issue is entanglement. When features in the latent space get tangled up, changing one aspect, like the color of a picture, might unintentionally affect other features, like the shape or background. This makes it difficult to control specific attributes directly. It's like trying to adjust the brightness of a photo without affecting the colors, but the controls are all mixed together. Smoothness is also vital. Small tweaks in the latent space should lead to small, understandable changes in the output. But achieving this smoothness is not simple, especially when data is complex or noisy. Researchers try to improve this with adversarial training, where models learn to produce more stable and reliable outputs, but that adds extra layers of complexity. Some models use discrete latent spaces, like dividing data into separate chunks instead of continuous ones. This can help with semantic control, but it makes the optimization process more difficult because the model has to learn to switch between these chunks smoothly. Finally, exploring and optimizing the latent space is a puzzle. Since the space is abstract and not directly interpretable, finding the right points to generate specific features or styles requires clever algorithms. Techniques like genetic algorithms or stochastic searches are used to navigate this space, but they can be computationally intensive and requiring careful tuning. In real-world applications like image generation or creative tools, controlling the latent space is essential for producing high-quality, coherent results. It allows for user-guided modifications and diverse outputs. But the difficulty in managing this space affects how well models can be fine-tuned for specific tasks, how reliably they generate new data, and how ethically they operate without bias or artifacts. So, controlling the latent space of variational autoencoders is a balancing act. It involves creating a compressed, smooth, and interpretable representation that can be manipulated easily while still capturing all the important details. This ongoing challenge is at the heart of making generative AI more powerful, flexible, and useful across many fields.